So we will discuss how to locate the shear center of some of the standard thin wall sections and a few numerical examples for that. So in the last video I have explained about shear center, its concepts, everything. So shear center, if you apply the load passing through the shear center of any section, then the twisting effect will be nullified. So only the member will be subjected to only bending or simple bending or pure bending. So that is the advantage. So if you locate the shear center of any section, then if you adjust the load so that the resultant or the shear force, you can say, if it passes through the shear center, then the effect of twisting will not be there. So in the case of unrestrained beams, normally it is subjected to torsional buckling and therefore twisting effect will be there. To avoid that, you can locate the shear center, and then if the resultant shear force passes through that shear center, then the effect of twisting can be nullified. So these are some of the standard thin wall sections which are used in steel design. So we will discuss how the shear center can be located in such types of sections. Here E is used. You can take this E as the eccentricity. So it is used as the measure of distance of shear center from the reference axis at a point. So the first one, I will take up a channel section. You can see that a channel section which is available in steel, it is symmetrical about one of the axes, or you can say it is monosymmetric section. So here you can see the ZZ axis, it is symmetrical about ZZ axis. Therefore, the center of gravity of the centroid lies along this axis of symmetry G, and shear center S. S is the shear center. So it lies somewhere here. So I will take the distance of this S from the center line of this web as E. So if you know these dimensions, all center line dimensions. You can see center to center line dimensions. So this is h by 2, this is h by 2, so the total is h, and d is this dimension, that is the width of the flange, and tf is the thickness of flange. Of course, this is also taken as tf. So both are equal to tf, web and flange thickness are tf. In such a case, we can derive that the eccentricity or the shear center is located to the left of this, in this case to the left of the center line of the web at a distance of b square h square into tf divided by 4 into iz, where iz is the moment of inertia of this channel section about this zz axis. So by calculating the iz and substituting here, we can get the value of E in the case of channel section. So another I section, which is once again symmetrical about one of the axes, I can take here. So it is symmetrical about ZZ axis. You can see here. So B1, B2, they are the widths to the center line. That is width across the center lines. And T is the thickness. Let us say T is the thickness. It has got uniform thickness for both flanges and web. In that case, eccentricity E. So of this shear center S from the center of the web, so you can see that it is h square T into b1 square minus b2 square divided by 4 iz. You can observe that this is similar to this expression where tf is equal by t, h square is same, only change is this b square is equal by b1 square minus b2 square, where b1 is the higher value of the width and b2 is the lower value of the width. So depending on the values of b1 and b2, the position of S will lie. Now the third one is the semicircular section. It's a thin wall semicircular section whose radius, of course, once again radius is measured from the center of the section to the center line of the tube. So it is R, and thickness of this is T, and E measured here is from the center. So from this distance OS is E here. So E is given by 4R by pi. Or if you put pi is equal to 22 by 7 and simplify, you will get it as 1.27 times R. That means you know the radius R of this semicircular tube, so E can be found out. Next, the fourth one is the split circular tube with constant thickness. See here, there is a split here, there is a small opening here. So the width of this opening is very small. when compared to the circumference. So R is the, once again, is the radius, S is the shear center here, it lies to this side. So E is the distance from the shear center to the centroid of the semicircular lamina. In this case, the shear center is given by 2 times R, or almost it is equal to diameter. Now the fifth one is six square tube. You can see it's a square and you can take it as a rhombus also. So B is the width of this tube, center to center width, and T is the thickness, uniform thickness you can say. And here G is the centroid lies here, and eccentricity E of the shear center from this end, from this point, from the point of intersection of the central lines. Here this E is given by, so this B width, that is the side of the tube, center to center, the distance of the tube divided by 2 root 2. That is the expression for E. Next, coming to split rectangular tube of constant thickness. So this thickness is constant here. In this case, so the shear center S is located at a distance E from the central line of this edge, you can say. So G is the centroid here. This E is given by, in this case, B into 2H plus 3B divided by 2 into H plus 3B. So H by 2 is the distance from the central line of this, you can take this top edge to this point, and H2 is this. So this is symmetrical about, once again, this ZZ axis. So symmetrical about this ZZ axis. So in this case, E is given by this formula. Next, coming to monosymmetric I section, which is nothing but similar to this. But here I have taken in the horizontal direction. Of course, I have taken B1, B2 as the widths of the 2 flanges, and T1 and T2 they are the thickness of the 2 flanges. And here web is this one. This is the web. Now in this case, the distance of this shear center from this edge is, I have taken as B1. And this I have taken as B2. So it is given by this formula. So E1 is given by T2 into B2 cube into H divided by T1 B1 cube plus T2 B2 cube. So this is the formula. And E2 also can be found out using this formula. You can see the difference here in the numerator. So T2 is replaced by T1, B2 is replaced by B1, and here denominator remains the same. So we can observe the difference. So once you know this E1, you can find out E2. So any one formula you can use. So remaining the other one you can find out by knowing the value of H. Next, H is this, center to center of this. This is H. Please note. This is H. Next, circular arc. Suppose if the cube is in the form of a circular arc, which makes an angle of 2 beta, separate angle 2 beta. Once again, it is symmetrical about this ZZ axis. This is beta, this is beta, and your central line radius is R, and D is the centroid, and S is the shear center. Here E is measured from the center of this circle. So OS is E value. Here E value is given by 2R into sin beta minus beta cos beta divided by beta minus sin beta into cos beta. Only thing is beta is in radians. It should be in radians. So degree should be converted to radians. And if you substitute here, you will get the distance E, that is the location of shear center from the center of the circular arc. Now there are some 2 examples I have given here. One is once again for the channel section. For the channel section, this is the formula we are going to use. So only thing is we need to find this value of Iz. So here you can see, so you have one thing very important is you have to take the central line distances. That is very important. So H is here. This 500 is over at 500 minus this is since this is 10 mm. So this is also 10. This is also 10. So you have to deduct 5 mm this side and 5 mm this side. So that gives the value of H. So H is this value. So which is 500 minus 5 minus 5, 490 mm. B is this value. Please note that B is this value from the central line of this to this. So this is actually 150. 150 minus 5. So that is 145. That is value of B. TF of course is 10 mm here. The IZ value, moment of inertia of this channel section about the ZZ axis. So you can take like this very simple formula. We know that the moment of inertia of a rectangular section of width B and depth D about the horizontal centroidal axis is BDQ by 12. So I will consider this as a big rectangle. So B for this big rectangle is 150 and D for this big rectangle is 500. So 150 into 500 by 12, and from that I have to deduct the moment of inertia of this portion. So I have taken moment of inertia of this entire portion minus moment of inertia of this portion. So this portion width is 500 is 150 minus 10, that is 140, and D becomes this value. So D is here 500 minus 20, 10, so it is 480. So 140 minus 480 whole cube by 12, that is the moment of inertia of this portion, hollow portion. So if you deduct this moment of inertia from this moment of inertia, you are going to get this value as your IZ of this channel section. Now by substituting the values of B, H, TF and IZ in this formula, you can get the value of E as 46.35 mm. That means the shear center lies at a distance of 46.35 mm from this center of this web. So this is where the shear center lies. So you can directly use that formula. Another example I have taken like this. This is another example I have taken. If you compare the values, so here B1 value he has given 100 mm, B2 value he has given 75 mm, and H value is actually center to center distance, which is nothing but 350 plus this is 5, this is 5, so it becomes 360. So H value is 360 and T value of course is 10 mm here. So these are the values, and only thing is we need to find out the IZ value. So B1 is 100, B2 is 75, H is 360, T is 10. IZ value, once again we have to calculate using the standard formula of moment of inertia for a rectangular section. So here what we have done here is, so this is for the web portion, you can see this is B and this is D. So BD cube by 12, so 10 into 350 cube by 12, that is for the web portion. And for these two flanges, so since the symmetrical, so both the flanges they are at equal distance from the centroidal axis, as well as they have same equal area. So 2 times, I can take 2 times, this is for 2 flanges, into here B becomes for the flange 75 plus 100, 175, into thickness is 10 mm, so 10 cube by 12, plus now we have to use parallaxis theorem, because we are writing the moment of inertia of these flange portions above the centroidal axis. So we have to use parallaxis theorem. So in the parallaxis theorem it states that this is plus area of the flange, that is 75 plus 100, 175 into 10, that becomes the area of one flange, into distance of centroid of this flange from the centroid of the I section. So that means it is this distance I have to take, that is actually half of this. So half of this becomes half of 350 plus 10, that is half of 360, which is 180. So square of that. So actually this is the parallaxis theorem we are going to use in the case of moment of inertia. So if you simplify that, you are going to get 1.49 into 10 power 8 millimeter power 4. Now substitute the values in this formula. H is 360 square, H square is 360 square, into T is 10, into B1 square is 100 square, minus B2 square is 75 square, divided by 4 into IZ is this value. If you simplify, you are going to get E value as 9.5 mm, that is distance of this sphere center S from the center line of the web. So this is the value of E, you are going to get 9.5 mm. Like this, any numerical problem can be, just by substituting the values, you can get the location of the shear center for some standard tubular thin walled sections.